and pretty much show you what a full stack quantum computing company is doing. But for those who don't know quantum computing, I also want to give a little bit of introduction to quantum computing. So how many of you are totally new to quantum computing? I'm curious. Okay, so some. Okay, good. So a good chunk of the talk will be for you, which is good, right? Because I have to convert you as an evangelist, right? So the rest is already converted. Just kidding. But let's go from there. Okay, so overview of the talk. We'll see how we can cover, if we cover everything, that'd be great. So first we'll talk about why is everyone so excited about quantum computing, concepts of quantum computing, quantum circuits. That's kind of like what we use in basic quantum computing hardware and software. And then examples, problems we work on, there are many more. I'm going to touch on some, and then I do want to talk about careers in quantum information science and engineering. So why is everyone so excited about quantum computing? Well, you can think about that and say, well, we have classical computation, right? We call normal computation what we're used to. And it went through its development. You know, we started with moving marbles on tracks, if you wish, to Mark I, which is kind of like our first electronic classical computer. And then we went on and made smaller and smaller machines until we have our desktop computer, and that's even out of date, right? Because we now have our cell phones that are computers in principle. So all my kids have our old cell phones, and that they're game computers. So we have all this, and then now we obviously have AI, and we have robots, right? And they're all powered by classical computation, and it's amazing what we can do, right, with classical computation, AI and machine learning. We have these big data centers. We have all these tools. So why do we need something else? And it really goes to how big is your problem, right? What is the order? Like, how long does it take for you to solve a problem? In principle, we can solve anything if we have infinite resources and infinite amount of time. But as we know, we don't have that. So as you know, optimization examples, that's kind of like the highest computing cost examples you can think of. One of them, if you just have like an aircraft and you want to have 10 different routes, right? You want to have 10 aircrafts assigned to 10 different routes. You want to optimize it somehow, depending on some kind of cost function, right? So how many passengers do you have in each airplane? What are queue costs, right? And such. So you want to optimize this. How big is your airplane, right? How full you get it. And in this case, it's 10 to the factorial, 3.6 million options, right? That's a big number, only for 10. And if you think about Delta Airlines, I just picked it for an example, it has 5,800 flights per day sometimes, right? So that's a huge number. That's a huge optimization problem. And with all of these options you have, so a classical computer in its simplest form would have to try each of these iterations one by one, calculate the cost function and figure out what's the best, right? So it's going to take a long time to go through all of different permutations and then figure out what's the best. We do have parallel classical computing, so you can have different nodes doing computation parallel. That's how we speed things up. But in principle, that's kind of like what you have to do. So that's kind of like one area where classical computing, even though it works, we don't have an infinite amount of time. So we have to figure something out that's better. This is kind of a plot a lot of people talk about in quantum computing and even in computation overall. It's this big O notation, the time complexity plot, where you have CPU operations versus input size. So you have a nice color code here. Red is kind of like where things kind of blow up quickly, and you, even if you just make your problem a little bit bigger, a little bit more complex, suddenly your GPU operations blow up, right? But if you're in the green area where something is like linear, right, or like a constant or log n, right, where n is kind of like the input size or your number of operations, if you wish, then you see this is kind of better, right? So when we talk about computation advantage or improvement or speed up, what we do, we typically walk from a problem that is initially has like an exponential growth. We want to make it go to this direction, like into the green area. So that's when we can say speed up. So we have a quantum speed up. We sped up the calculation somehow that we were able to move to a different O, right? So like maybe we can go from x squared to a linear, right? Computation expenses. So that's what we want to do. So that's kind of like the exponential speed up you hear sometimes, the quadratic speed up you hear sometimes. It always goes back to this plot. So with quantum computing, what we want to do is we want to take something which is blowing up classically. We want to bring it to the green area so we can actually compute it in a finite amount of time. Okay, so this is kind of like the introduction. That's why we are excited about quantum computing, especially those who believe in the technology and believe that we're going to make leaps in this. So concepts of quantum computing. So again, I have a lot of things to cover, so I will only touch kind of the high level. But quantum computers compared to classical computers using the laws of quantum mechanics. And what do I mean with here that you use these laws to store and manipulate information. So in essence, what you have something that is subatomic, something on a subatomic level, like an atom, for example, right? And then you're trying to manipulate energy levels within the atom. And for example, one energy is your 0, and your 0 bit, we saw called actually like an atom would be a qubit, and then you have 0, which is the classical 0, and then we would have a 1. So one energy level in your atom is your 0, and the other one would be a 1. And then you try to figure out, just like classical computation, what zeros and ones you're getting, and that hopefully is going to bring you answer. So that's one thing that we actually use computation on nature. That's what we like to call it, like on something that nature gives us. It's perfect, it's pure. Could be a photon too. And you can imagine like different polarizations being the different zeros and one, right? But that's very exciting. So now we have to use quantum mechanics in order to understand how to store information, how to manipulate the information. And there are a lot of different concepts in quantum mechanics. The first one you have to understand is something called superposition. And this is, you hear a lot, and it's difficult to explain. And the way one can think about it, that's in classical computation, you have a 0 or a 1. It's a deterministic process, okay? You start with a 0 and a 1, it's the way it is, right? So in a classical bit, it could be a 0 or a 1. A quantum bit, on the other hand, is a little bit more complex in the sense that you have a superposition of these two states, and it can be in any superposition. And the way we think about this is mathematically, we can actually do the mapping. It's something called a Bloch sphere. And it really comes from spin ideas. But the idea is that you have a qubit which is in all possible states at once. And only if you measure it, the qubit will collapse to state 0 or collapse to state 1, right? You don't know what it is in between. So in between is a superposition of 0 and 1. This superposition can have some kind of probability to favor one state or the other, but it's always a superposition. And this is why quantum computing is powerful, because you have not just these 0 or 1s, you can be in both states at the same time until you measure it. And mathematically, I'm first going to look at show you mathematically. When you take quantum mechanics, you probably heard about the Dirac notation. Have you heard about Dirac notation? Some of you, not all of you, some of you. But if you go to quantum mechanics, we'll talk about Dirac notation. We talk about the wave function and wave vectors. And psi, the top row, you have one qubit, and you have the 0 and the 1 state. So one qubit can be in 0 or 1, right? It's superposition, and the C1 and C2 in front, these are your probability amplitudes. So you square them, that gives you the probability. So C1 squared is the probability being the 0 state, and C2 squared is going to be the probability being the 1 state. So the point is that you have this wave function. So you want to, whatever classical problem you have, you want to somehow map into this wave function, which you can represent in terms of qubits and probabilities. So now when I talk about superposition, you have 2 qubits, 4 qubits, and n qubits. So for 2 qubits now, they can be in 0 or 1 at the same time. So now you have a superposition of 0, 0, 0, 1, 1, 0, 1, 1. Each of them have a probability in front of them. So this is 2 to the 2. So you have 4 states. So now you go to 4 qubits, So it's going to be 2 to the 4. 2 to the 4 is what? 16, right? So now you have 16 different states you can be in, right? So 4 qubits, you have 16 different states you can be in simultaneously. If you go to 50 qubits, you suddenly have 2 to the 50, which is now like terabar meters in essence. And that's, if you convert it, I can't convert it, but someone did the conversion, and it's pretty much 9 petabytes of RAM. It's a big number, like I can't even capture it, but it's 50 qubits have that much potential, right? In RAM, which is just amazing. But it all comes from the superposition, and you will work with this in quantum mechanics, and you will learn how to do this. And it's all about linear algebra. It's kind of like telling you the math for it and how it works when you start to manipulate these wave functions and figure out probabilities and such. But the main point here, to emphasize it again, if you have a 10-bit string, classical bit string of 1, 0, 0, and 1s, right? You have 2 to the 10 possible states at one given time, right? So your zeros and ones can switch, but it gives you the 2 to the 10 possible states at a given time. You don't have them at once, you only have them at a given time. So imagine one of them is always a solution to a problem or something you have to check, right? It's one thing you have to check, and then you change the state, and then one thing you have to check. You change the state, and you have to check it again. Or the bit string, I should say. On the other hand, a quantum computer, you now have 10 qubits. And so you have the 2 to the 10 states all at once. So you can encode your problem. In essence, you have a lot of different things, a lot of different solutions you could look at once, compute at once. And then you hope that you somehow can make a smart algorithm that your correct solution will fall out or will stand out in that sense. So this is kind of like just showing you in terms of possible states you can have compared to bit strings and qubits. But it's just, very, impressive. Don't count the squares. I don't know if that's right. Okay, so now if you go into computational chemistry and you want to, model something fully. So if a caffeine atom, for example, 24 atoms, caffeine molecule, 24 atoms, and you want to fully model that molecule, right? Fully model it. You would need, for specific, approximation you're doing or specific calculation, fully model it. You would, no approximation, I should say, you need 2 to the 160 classical bits. And that's just 1 to 10% of the Earth atoms. That's like a comparison that sometimes is shown. And if you then go to qubits, depending on your orbitals, right? Then you only need 160 qubits in order to do the same thing you would do in a classical, right? So I told you a qubit is could be an atom, right? Or an ion, right? Or a photon. So you'd be like, wow, I only need 160 photons, right? And I can calculate this. The problem is that our qubits, our computation we do in a quantum computer is very, 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 very noisy. So unfortunately, we can't do that yet, right? So we're not there. We'll talk about noise in a little bit, but that's the idea. So if you go to penicillin, which is a very important molecule for us, just thinking about how many times it comes up in healthcare, it would mean like, the observable universe, the size of that, and it's just too big compared to 286 qubits, which seems to be reasonable, right? So anyways, there's calculations that go into this. Don't take the numbers for, the truth, but it just gives you kind of a scale. That's why quantum computing is so exciting. Okay, so any questions so far? Yeah. Just a hydrogen, H2, I think you can do it, depending on, there is some approximation that goes into it. I think it's maybe 4-ish, somewhere there. Yeah, but there's different, you can have 2 or 4, you can take the, advantage of symmetries, and then you can cut the number of qubits down. But yeah, so it's in a reasonable, I think it's 4 for H2, yeah, for the Hartree-Fock approximation.
Did you return to the previous counting molecule? Yeah, I wonder if it helps students at all if you're referring to the nuclear spin on the various nuclei, the hydrogen.
Yes, so you can refer to that, I think, yes, yeah.
Spin on out. That's how I heard this.
Yes, so you can think about the different levels that are filled, yeah.
Yeah, I never feel spin.
So obviously the different modalities of quantum computing, and I will focus on quantum circuits because that's the mostly used, but you have different ways of programming a quantum computer. So for gate-based quantum computers, we use quantum circuits. So pretty much what happened is that we again kind of like look at the classical way of computation, so logical circuits. So that's a very, very, very simplification of how chips work, right? You have some kind of gate, you have a transistor, you put in some voltage, and depending on how you set up your transistor, something comes out, right? You define a 0 to be like 0 volt, a 1 to be a 5 volt, which is saying something. It could be 2 at 1 volt, right? It could be 0 and 2 volts or whatever. But it says like 0 is maybe 0 volts, a 1 is like a 5 volts, and then you send something in, right? Different signals in. You maybe want to add you want to do something with your zeros and ones. You're sending in into your gates, and then you're adding these gates. Each of these gates do something to your voltage level, and then that's how you have different gates: NOT gate, AND gate, XOR gate, and you put these gates together, right, to make your algorithm. So you can add these gates together to have an adder. To add numbers, you can add these gates together and more than I show to make multiply numbers together and such. So that's what you do on a logical circuit. So similar to kind of a logical circuit, we have a quantum circuit, which I show here. So in this case, you have, for those who haven't seen this, so this is a quantum circuit. The boxes we call gates. Here at the beginning, we're going to initialize the qubit. So these Q0, that's a qubit, Q1 a qubit, Q2 is a qubit. Then see these here, these are we call classical registers. So we still have to read out our signal from the qubit. So it can either be a 0 or 1, where it collapses to the 0 or it collapses to the 1. So the classical register will either get a 0 or 1. Typically, each qubit has a classical register, but sometimes we have ancilla qubits, which we need for computation, which we don't read out. So the gates here, this is our algorithm. A combination of these gates is the algorithm, and then we measure the signal out. We collapse the state vector on the block sphere. So the H, this is called a Hadamard gate. It brings your qubit into superposition. So initially the qubit is initialized in a 0 state. You apply a Hadamard gate, it brings it in a superposition of both qubits. These ones are called the X0 gates. I didn't talk about this, but entanglement is another principle of quantum mechanics, which we use in quantum computing, where we entangle two qubits, right? So the idea is if qubit 1 is in a certain state, then qubit 2 is either switched or stays the same. So a lot of these entangling gates, they're typically connections between two lines. You can also have topology gates, which connect 3 qubits. You can have other gates that connect 4 qubits, but they're all entangled. So what you can say right now is that you're doing initialize your state. So it's kind of like logical qubit, you're setting in a 0 or 1. Then you're doing your algorithm, right? Which is quantum mechanically an operator. So if you study quantum mechanics, we do actually operations on the qubit. And then you read it out into your classical register. So this is a quantum circuit. So when you talk about taking a classical problem, you want to have this quantum circuit in order to be run on gate-based quantum computers, which are superconducting quantum computers or trapped ion quantum computers. So this is a quantum circuit, and that's you always read it from this line to this line. Okay, so you always go from left to right in time. And then obviously it's a probabilistic outcome because you have these probability amplitudes. So you have to run this circuit multiple times to build up statistics, right? So in this case, you have 3 qubits. So you have 2 to the 3, which is how much? 8? Yeah. So we have a pen here. Yes, not. That's okay. Yeah. So pretty much you have. So you have your 1 0 1 1 0 0 0 0 1. You have 8 of these, right? Options. And then typically what you do is you have your frequency, right, of a certain state. And here you have your states. So maybe this is this, this is this, 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 this. Just doing something, right? So this could be your 1 0 1. This could be a 1 1 1. Typically they're lined up. I'm just mixing them up right now. But maybe the 0 0 1. After you run it 100 times, this will be building up, right? So this state here, this bit string, quantum bit, like quantum for your state, the 0 0 1 state, right? So qubit 0 is in the 0 state, qubit 1 is in the 0 state, and qubit 2 is in the 1 state. That is the most likely, so that might be the solution to your problem, depending on how you programmed it, right? So because you have this probability, you have to run your circuit once, reset your qubits, run it again, twice, and so on and so on and so on. So you do it typically 100 times, sometimes 1,000 times, sometimes 50,000 times, sometimes 600,000 times. So you run it many, many times, depending on what statistics you're looking for and how noisy your computation is. Okay, and obviously, even if you run it 1,000,000 times, if it's too noisy, it's just junk. There's nothing more you can do. You're just out of luck. So this goes back to I'm just flashing this to let you know that you have your bracket notation, and you can map that onto your block sphere if you wish, with your typical math tricks. But in essence, what you do when you run this circuit, which I showed you before, is you take your initial vector on a block sphere and you apply a gate, and then you rotate it on a block sphere for a certain angle, on the block sphere around a certain axis, right? If you have 2 qubits, you may rotate them together, like you rotate this one based on what this one is in a state. So this is the entanglement. But pretty much what you do for an algorithm, you keep rotating and rotating until you applied all the gates, and then you measure it out. So all of these gates are matrices. So if you have a single qubit gate, you only do rotation on one, the Y gate, for example. This would be a matrix you can implement when you do linear algebra. So this is something I want to say, with a few number of qubits, say 30 qubits, 32 qubits, you can actually just put that into a classical simulator and calculate the state vector of your state of your function, wave function. So you can just put that in. It's pretty much matrix multiplication. Your classical computer can do that, right? But imagine you have 50 qubits, right? You have a huge matrix you have to work with, because when you have 2 qubits, you entangle them. It's a 4x4 matrix, right? And then you keep going. So in any case, this is where the limitation is, but up to 30, 40, 50 qubits, we can simulate that classically. That's what I just said. You have a problem, superposition possibilities. These are multiple qubits superimposed, should be 4 spheres by themselves, but pretty much they represent a quantum circuit, and then you run it on your quantum computer to get out a state. Okay, so this is kind of a principle. I know I went over fast, but the idea here is that you take a problem, you figure out a wave function for the problem. You try to look at the wave function, right, and put it in a kind of a bracket notation, if you wish, and figure out the matrices and what kind of gates you would have to apply in your algorithm to make a circuit. Then that's what you run on a quantum computer to get an output, which you have to sample many, many times in order to build up your statistics. So given that you have an algorithm, now you have to implement that in a quantum computer. And there are many different quantum computers out there: superconducting, ion traps, photonic, and other technologies, right? Ion traps could be also that there's neutral atoms. There's a lot of like different qubits. Mariana is one of them too. So in any case, there's different modalities. Superconducting and ion traps are the most developed right now. And then your photonic is probably coming up next. And then you have all other modalities. Right now, in industry-wise, the ion traps have the least amount of error. The superconducting computers have the most qubits. Okay, I'm not talking about annealers because that's a different, a little bit of different technology. And then obviously with these more exotic technologies, we have shown in the lab that we can get very, 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 very good qubits. Okay, so, but they have not been now integrated in a big quantum computer where we can use them. So there's a lot of potential, there's a lot of research being done, and it's an exciting area. So you have all of these quantum computers, right? They're all different. This is superconductor, this is trapped ions, right? And they all look different. So this is the IBM, the chandelier in here. Actually see it inside. So you have to cool the system down, and then the dilution bridge, we call it, and then here at the bottom is your chip, right? So you actually, each of these levels is like a step down in temperature. You keep going down. So there's the IBM quantum computer, and our Quantinuum quantum computer is a trapped ion quantum computer. So it's lasers that we use for applying the gates and to do computation. To give you even a better, this is a good picture, right? So this is fairly nice. You have the control system, right? It's the size of a person. Superconducting is really nice at the moment. This is the scale of a trapped ion quantum computer. So you have two optical tables that are full of optics. You have two different levels on top of the controls. So if you see a trapped ion quantum computer, it's very much feels like still like in a lab setting, but it's a commercial system, right? So it runs very well. It's very finely tuned. It's a piece of art if you go in there, because of all of the pieces you see, and they all have to play together in order to manipulate single ions. Just to let you know, here is the ion trap in here, and the chip we're doing computation on is the size of a grain of rice. Okay, so size of a grain of rice, that's our chip, and we need all this to control the ions, right? So it's amazing. So this is our trap, and I hope the movie plays. Yes. So this is our newest trap, ion trap. It's our H2. It's like a racetrack. And I actually have to, it's a racetrack, and I think Spendier just has a 200 ion trap, and they call it Enchilada. Spendier National Labs in New Mexico. I thought it was so fitting. And I didn't know, and I read up, and the previous was called Roadrunner. So you know that there's a Roadrunner going between Albuquerque and Santa Fe. Yeah. So anyway, so we have our race trap. It's at 32 qubits. These are commercially, right, running. So right now, you can go on a cloud and you can do computation on this machine. Okay, so this is running. We have it offline every so often for upgrades. But these are 32 qubits going around. These are singly controlled qubits. We move of them, all of them singly. And that's the beauty about trapped ion quantum computers, because you can move them around individually. Yes. Yes. So you as a university, as a professor, you have to we have partnered with Oak Ridge National Lab for research purposes. So for class teaching, the trapped ion quantum computers are how should I say, they are very how should I say, so we don't have that many trapped ion quantum computers that we have superconducting quantum computers. So IBM actually has a free account you can access to for teaching. It's a very good for things, yeah. So we can't make it available to everyone because we just don't have that many machines. But what we do for research purposes, where it matters that you have good qubits and we have low noise, right? For those, we make it. You can apply with Oak Ridge National Lab. You can submit a proposal, and they are our hub. So they're giving out free access to all the academic programs. So I have a link up later. So you can they have this called QCup in Oak Ridge at Oak Ridge National Lab, and they give access to our quantum computer for free. Okay, so yes, so going back to the chip here. So you see this here, these vertical. So these are these lines here, the parallel lines. These are two RF rails, and then these horizontal lines. I'll find my mouse now. Where is it here? Maybe we should do. Here's a pointer. And these horizontal lines, these are our gate zones. So this is when we have to move an ion into here in order to do a gating operation, to do our rotational Bloch sphere, or we have to move 2 ions into here in order to entangle them. So we have these 5, actually 4 gate zones here. So in a linear trap, we had 5, but here we have 4 gate zones. So there's something called the ion dance. So we figure out, once we submit the circuit, we figure out what's the most efficient way of moving these ions around for the computation to go into the different gate zones. Once we load an ion, we actually get their own trap, the ion trap. And we have these RF rails that make the potential wells and we trap the ions. Ytterbium atom is our ion. And 2 hyperfine levels is one is 0 and one is the 1 state. We also actually have a barium atom, a barium atom with ytterbium. We use the barium for sympathetic cooling. So we keep that barium ion very still, and it also like cools down the ytterbium ion. So we actually move around like a chain of ions, with 2 ions in one chain. And if you wanted to entangle, we have to move the 2 wells together, and then we entangle the ytterbium qubits, and the barium come with them for cooling. And then when you want to do engage or you want to initialize your qubit, we put in laser beams. So to kind of like illustrate this here, this should be a movie, but I apologize, just don't want to run through it. But you have 3 qubits. You initialize first with the initialization beam, then you apply 2 Hadamard gates. So these 2 qubits have a laser beam coming in to apply the Hadamard gate. It's a certain rotation. So you can imagine you have to play with frequencies, right? Depending on what you're doing computation-wise. And then you also have to play with the duration, right? So how long do you apply the pulse in order to rotate it less or more on a Bloch sphere? So here we apply the gate, the Hadamard gate. Then we want to entangle qubit, the red one and the green one. What we need to do is we actually have to move the green to the red, and then they're together. And now we apply 2 wafer beams, we entangle them. Then we can actually want to do the red and the blue. And now we would have to move the red to this side, and then we have to move it to the blue, and then we do a favorite laser beam. So we actually move them physically around. Yeah. I have not heard about it. We're trying to do pretty qubit. I think it's more about the combining the potential wells. it's not that trivial because you actually have, you know, when you combine them, you have this hump, and then you have to do it right at there, like the minimum again. So it's I think having actually 3 rails to combine probably definitely needs a different ion trap. There are people that think about 3D, right? 3D, making a 3D trap, where you have this extra level. Maybe then you can bring in 3 qubits. Also called QDITs, like where you have like instead of 2 levels, you have multiple levels, right? Energy levels you can play with. So there's a lot of different ways one could think of. But that's the one that's implemented right now. It seems to run.
So if you're only able to have, it looks like you're only limited to doing these gate operations on errors. Does that limit the access to the full Hilbert space?
Oh, you're asking something that I can't understand. So I don't know. Yeah. So nearest neighbors in the sense of.
Yeah. So like, it looks like from the diagram that you couldn't bring blue and red together.
Oh no, you can.
Oh.
Yes. So what you do? So here actually you blink blue, red. So actually what you do in a quantum computer, you actually can watch that. So it's just like you saw the ions going around. You have this qubit and you can actually swap them. Physically swap their position on the chip, and then this one goes this way and this one goes that. Yeah. This is different for a superconducting chip. A superconducting chip has the qubits set in space, right? And you have, if you want to like have this qubit talk to this qubit, you have to swap through the chip with 2 qubit gates. It's like an entangle to get the message there. In trapped ions, you just bring them together, right? But you're confined to the rate, like to the trap. You have to do the swap gates. It all takes time, right? So it's slower than superconducting, obviously, because of that. So you are trading in speed for less a number of gates and for higher quality qubits. Okay, so this is something you see a lot. So everyone says we have the best quantum computer. Our errors are the best and the smallest. So this is called a fidelity. So when you apply a 1 qubit gate, the fidelity of this 1 qubit gate in our trapped ion is 99.9998%. We think that's pretty good, but classical computation, we talked about it, right? It has like billions or something, right? Billions, right? So this is 1 out of what, like this is 100,000, 10,000, 100,000, right? So billions is still way bigger. The 2 qubit gate fidelity is 99.8. That looks also good, but we'll talk about this in a bit. So you want to have this right now. People say if it's at 99.9, you're starting to get in a very interesting era for quantum computing. So this is when you entangle 2 qubit, that's the gate, the error. And then you have all of these other errors, memory errors, crosstalk, and such. But what is this about, this error about? Why should we care about this error? And if you take something away from this talk, besides, quantum computing is cool, I want you to take that away too. So when you are actually running a quantum circuit on a quantum computer, if you get to the point, you sign up and you would like to know if your result is going to be any good. All you need to do is count how many 2 qubit gates you have. So going back to the circuit, right? You have the circuit. So how many of these do I have? Where I entangle 2 qubits, right? So how many of these do I have? You count how many 2 qubit gates you have in your circuit. And then you take the fidelity we just talked about, the 0.99. So 99% here is 0.993. So 99.9, sorry, 0.99. That would be 99.3%, which is 1 would be perfect, 100% would be perfect. So you have 0.9993, for example. You take this 2 qubit fidelity and you exponentiate it to the number of 2 qubit gates you have. You calculate this percent error from this equation. So just to give you an idea, so if you have 0.991, right, that's 99.1%. This is the brown, is kind of your trajectory. total number of this is a 2-qubit error. Just say you want to have something with 25% error. You can only apply 31 2-qubit gates, and then you already have that error. And that's not much. The high H2 atom, H2 molecule, right? H2. If you just have a circuit, one circuit describing the energy, the constant energy, and you have to like run it through a minimization routine, only this circuit 150 total gates and 56 2-qubit gates. Okay, so if you have 56 2-qubit gates, you already have here like almost 40% error just for the H2. But if you can bring this closer to 1, right? So now you have 99.8%. That's where trapped ion lie. So we are kind of in this area. This is where superconducting qubits lie. So suddenly you can do, 142 qubit gates before you get this error. So now these are physical qubits. These have noise. So now you can use physical qubits to make something called logical qubits, right? So logical qubits may have 0.999, right? But you need like 10, I'm just saying like maybe 12 physical qubits to make 3 logical qubits with a better error. Then suddenly we can implement logical qubits in our machine. They're still not perfect, but they're better than this number. We can do almost 1,000 2-qubit gates, okay, for chemistry applications. So that's where we are right now. It's around 1,000 2-qubit gates, which we can do in chemistry applications that still give, meaningful result, but classically you can still simulate it. So there's still that area. So typically, our scientists if they get to 50%, that's kind of like where they say, if my algorithm I developed has 50%, then it's yeah, we do stuff with 30 or 40. It's all about how you collect the statistics, right? So how many shots do you have to make? So if you have something, if you have many qubits, right? Then everything's just gonna be a 0 or 1. So if you get 2 shots or 3 shots in that thing, it is very unlikely that you get that, right? So there's statistics that come into play, and they run that number, and
they don't have to do it correctly. They just repeat and look at
yeah. So there's typically for correction, what we do right now is actually called error detection. But there's one way of doing it where you detect the error, and when you detect it, you just stop the run. You don't complete it. We do have error correction in the sense of we are measuring out a syndrome and try to correct for it, but there's this qubit overhead. So in order to do like 3 corrected qubits, you need to have 12 physical qubits, right? So you have this overhead. And then every time you correct something, you have to reset it or something. You have this qubit reset, you have to do the mid-circuit measurement, and then you have coherence time. Your qubit goes blah after a certain time, right? So you can't use that anymore. Then you still have to apply these gates. So it's just, you have trade-offs here and there. Some algorithms like something better than others. So it's a lot of art too right now. I think that you figure out what works well for your machine, for your architecture. Yeah. But yeah, so this is kind of what researchers say, if you have 50% 2-qubit error, just don't even bother running on the machine because you probably get just noise out. Okay. So where are we here? So the number of qubits. So we have around 100 here, right? How deep can we go? Like these 10,000 maybe gates, overall layers. And really where we want to be is kind of like for human DNA sequencing, we want to be high in this area. So we want to have 1 million layers deep with 100 qubits. But if you want to worry about cryptography, someone like hacking your codes, your passwords and such, you really have to be up in this area. So you're gonna get there hopefully one day, right? But you're gonna have some time. So just to give you an idea where global search and Shor's algorithm kind of like hovers compared to where we are right now. Here. Okay, I'm just gonna keep this because I'm getting down. The only thing I want to do now is one thing we're doing is when you run now a algorithm, your algorithm you want, you prepare a quantum circuit. You also have to consider how do you map this quantum circuit onto your quantum computer. You have to consider the architecture of your device, and then each device, unfortunately, can't apply a universal gate set. So we can't apply a Hadamard gate on an IBM machine or on a trapped ion quantum computer. So we have to take this Hadamard matrix, which is a 2x2 matrix, specific matrix. We have to rewrite it into the gates we can implement on a quantum computer. So that's why gates are typically called unitary, so you can rewrite them into other gates. So your software, for us, we have TKET, or we take Qiskit or such. They take these circuits and they map them on the quantum computer. So these circuits then are sent to the machine and then to the quantum processor. So this is what the software stack does. I just want to quickly say that you need software that takes the algorithm. You need software to produce the algorithm. Then you need software that maps the algorithm or the gates onto the machine, onto the basis gate set and the architecture. So this quantum Fourier transform, which is 1, 2, 3 qubits, becomes this many qubits. It says 3 qubits, but this many gates on an IBM machine. So you can see that you went from a few gates to many gates, and the amount of 2 qubit gates here is because you have to do a lot of swapping throughout the chip. Okay, so let's see. Let's call it full quantum computing stack here. And then when you're doing computation, one tool Quantinuum has is that's called TKET. This is a quantum SDK we are using, just like Qiskit is, but it allows you to take your favorite language you like to compute in, like Qiskit or like any kind of, this is all Python, and it convert it then to the architecture of your quantum computer. Okay, so it's a Python package you can install if you're interested in it. So just want to say a couple of problems we are doing. So we're working on biomarkers. So we're using our algorithms on a quantum computer to start to test, can we take the classical problem and can we learn something by developing drug efficiencies. So we're working with Crown Bio, JSR Life Sciences, and they all have like kind of pilot projects where they test out the quantum computer. Kind of they want to know how many qubits do I need and how good do the qubits have to be in order for us to run a quantum simulation that is useful. We also work with Deutsche Bahn, where we help them try to like optimize the train schedules. That was also a use case we worked on. And then obviously computational chemistry. So we're trying to calculate the ground state energies of different molecules and see how far we get compared to classical computation. Now I just want to flash this up. If you want to go into the quantum computing career, there's many companies all over the world. They all need you. And this is kind of interesting right now. If you look at these different companies, they have been polled. How many of you have a physicist, just PhD physics? They said yes or no. Almost 95% of the companies had their PhD physicist, which is pretty cool. Then bachelor's in engineering, almost 50% of companies have these. And then masters, you can see, so chemistry, right? So you can see you can use a lot of different backgrounds. And PhD physicists right now the mostly utilized because just you're building a quantum computer, it's all based on quantum mechanics and you're developing these quantum algorithms. So quantum mechanics is, physics is needed a lot, but eventually this will probably change more to engineering when we try to build more and more of these machines and run them. If you look at our full stack thing, so we have cybersecurity, quantum chemistry, and AI machine learning. TKET is our software stack. And then on the bottom here, you see the quantum computers. So researchers are typically spanning all of them. and project managers, they span all of these layers. Facilities is mostly, working with a quantum computer. Sales and business development, these are more, they talk to industry partners a lot. Then we have the community support. That's kind of like a software. We try to support the quantum computing community. And then kind of legal, accounting, administrative, marketing, HR, IT, that kind of spans everything. So a full stack quantum computing company needs everyone in any kind of degree you can think of. And they all are welcome in our industry. So starting now, September, we're going to have an internship available. So it's not posted yet, but you should check. This was last year. We had a 12-week on-site program. It's a paid internship. Interns work with the technical teams they are supporting. The work is meaningful. We don't throw them away. And just roles we filled this summer were optical and engineering, software engineering, electrical engineering, mechanical engineering, systems engineering, PhD, R&D scientists that the physicists falls into, HR, operations, labor fact. So we had like 30 interns, and I think our conversion rate was almost 20% that got a job. We have high school students, 2 PhDs. Okay, and then with this, I just want to flash out the resources. This is the link to get access to our quantum computer for research for free. That's our TKET manual for quantum SDK in case you're computing and you want to make sure you reduce the number of 2 qubit gates. TKET is really good at that. And then here you also have the link for internships. And I'm almost at the end and saying thank you. We had some questions answered.
We're going to prioritize students first. Carla, you have an update on what type of problems can you solve with the computers without writing?
So what type of problems?
Problems.
So we do a lot of like quantum chemistry right now. So we're trying more like look at the electronic structure, fine-tuning things. That's quantum computer is very good. If you look at like coarse grain, material science questions, quantum computers are not good at. Optimization wise, we're looking at optimizing, as I said, like a train schedule, for example, or optimizing where you have oil wells, for example, pipeline and such. So there's a lot of work going on there. And then for cybersecurity, what does it say? But we actually use a quantum computer to generate a random. It's not fully random, but like a very hard, like very hardened, like key, like it's better than classical like ways of making quantum keys, like key distribution. So we make these keys that then are used as seeds for to provide keys, for example. And then we do quantum machine learning. We're doing quantum Fourier transforms, which is like an application. So when you can map PDEs, you do partial differential equations. So problems you can map in the partial differential equations, you can solve that on the quantum computer. But all of this is still like very exploratory, right? So none of that has shown quantum advantage, where it's better than classical computer.
So this is for software simulation and this kind of paper is there any like physically build like a small testing or you use it to research labs?
What do you mean? Say it again.
So we have this simulation software like TKET or TKET or it's online and testing. So is there anything you can build like a small concert and testing or technically that labs?
What do you mean like with the center the cloud?
Yeah.
I think people, they build 1 or 2 qubit systems on an app. I've seen that. I think there are currently like quantum computers who have 1 or 2 qubit systems that happen on that, so we can build. But anything bigger than that, I think it's hard to, commercially. It's a really big undertaking. I don't know if the university will have to figure it out. I don't know. I can answer I know people are doing it. I know people are building superqubits in a lab, but they're very, very good. They possibly have 2 qubits, but I think it's no big, like 30 to 10, 30, 20, 100 qubit machines. I think people do at university level without maybe buying something from industry.
Maddie?
So, kind of mentioned that it is visible and logical. When you were talking about how many people it takes to be able to run those with the tapping model, is
That's a perfect qubit. That would be like a 1, like a 100% fidelity, perfect fidelity. Those would be a perfect qubit. To be far away from that, right? Because 1 in 1,000 times you have an error. That just adds up too much. So even the logic, we say logical qubits we have right now, it's not perfect, it's 99.9%, right? But it's better than the physical qubits. So we're starting to, it's better than 99.8. It's a little bit better, right? But it's a little bit better if you exponentiate, you actually can get really far out. So if you go back to this, yeah, all the way back, maybe this is easier. If you go here, just to appreciate this, this was the plot I want to show. If you have 99.9, your curve is like this, right? You suddenly can do like 200-300 2-qubit gates before you get 25% error, only by having this 1,000th better, right? So.
so you may have answered this already, but what is the reason that your trap lines could run around the track? What's the benefit?
That's how you can connect them fully. So when you have go to this picture here. I don't know, it's kind of like out of time here. You have to call it. I can always take the questions afterwards, right? But this is the chip, right? So when you have a superconducting chip and you want this qubit here to talk to this qubit here, you have to do like an entanglement of all the qubits through the entire chip. It's called a swap gate. So a 2-qubit gate of 2 qubits that don't, a swap gate is actually like to swap 2 qubits in a circuit in here. So to swap these 2 qubits, that is 3 2-qubit gates, which have error. So if you have to swap 4 qubits, you have to do 12 2-qubit gates, and these are error. And I showed you before that like 32-qubit gates, and you're only like 35% error. So the good thing about a racetrack is I can take this iron here and move it all the way to this one. And I have to do any swap gates. There's no 2-qubit gates I have, even though there was like maybe 20 qubits in between us. Every time this qubit was here, a qubit I don't like, I just swap, like I physically moved it around. The next one is coming up. I physically move it around till the qubit is there and want to talk to it. But I didn't do any operation that cost noise. The movement does a little bit of, I lose time, but on a noise budget, it's like orders of magnitude, less noise added to the circuit. So that's why we want to do this.
That is our time. Will everybody help me thank Kathrin Spendier today?
Thank you. Yeah, if you have questions, come up and ask me, and